Today's paper is Rethinking the Truly Unsupervised Image-to-Image Translation, also called as TUNIT. The authors of the paper states that the proposed image-to-image translation method is truly unsupervised, meaning the model does not require a labeled or pair of images to train the network. The paper targets to solve three problems, which are to identify domain characteristic of images, encode content and style of an input image, and learn a mapping function from one domain to another. The figure shows the overall architecture of the GAN model in the paper. Like other typical generative models, the model is composed of generator and discriminator networks colored in blue and red, and a network called encoder, also called as a guidance network in the paper, predicts and encodes pseudo-label and style of an input image. Given an image is first fed into the guidance network and produces pseudo-label and style vector. The pseudo-label information is used to help the multitask discriminator network to distinguish real and fake samples in the domain, while a style vector is used by the generator to produce translated image in a different domain. Let's first talk about the guidance network. The network takes an input image and outputs a pseudo-label and encoded style feature. To generate a pseudo-label, the authors set the possible image class K large enough to cover a number of classes present in the dataset. The guidance network is trained to group similar images to have the same labels. This is done by maximizing the mutual information of an input image X and augmented image X+. As shown in the equation, maximizing the mutual information lets the guidance network distribute all samples as evenly as possible over K domains. P represents the softmax output of the guidance network. Optimum is reached if H of P is maximum and conditional entropy H of P given P plus is minimum. And the loss function for the mutual information is follows. Pi denotes the k-dimensional marginal probability vector, and Pij denotes the joint probability. The guidance network also outputs a style encoded vector to help generator produce better looking outputs. The equation shows the style loss function used to train the network. S denotes the style of input image X. S and S plus in the equation is the similarity of the positive samples, and S and S minus pairs show the similarity of the negative samples. Note that the negative style codes are stored into a queue using previously sampled images. By taking into account the negative samples, the network is able to pull up the performance of the classification accuracy. Here are some other loss functions used in the paper. First, the model uses adversarial loss. This loss is not that different from the loss function used in typical GAN models. The output D denotes the logit from the domain-specific discriminator, and S tilde denotes target style code vector from the guidance network. The generator G learns to translate input image X to the target domain Y tilde while reflecting the style code. In order to prevent the degenerate situation where the generator ignores the given style code vector, the model also uses style contrastive loss. The loss function guides the generated image to have a style similar to the reference image and dissimilar to random negative samples. Lastly, to ensure generator reconstruct the source image X when given with its original style S, the model uses a reconstruction loss. The function not only ensures generator to preserve domain invariant characteristics like pose of its input image, but also helps to learn the style representation of the guiding network by extracting the original style of the source image. The final loss function is presented on this slide. Lambdas are the hyperparameters. To learn more about the training process, refer to the paper in the description. Here is a figure showing the performance of the method. On the left, TS&E visualization of the style space is presented. The model is trained on AFHQ wild dataset. Each point clusters represents the pseudo-label output from the guidance network. As shown in the figure, number of domains k is set higher than the actual number of domain in the dataset, but the images that seem to lie in similar domain are closely positioned. The figure shows image translation results on AFHQ dog dataset. On the left is the source image, and given the information of the target domain, the image is translated similar to the image in the target domain. Here's another figure showing image translation results on human dataset. On the first column is the source image. Note that in the third column, people in the target domain wears eyeglasses. There's a slight change in texture, but the source image is translated to wear eyeglasses. In summary, the authors argue that unsupervised image-to-image translation should be done without any supervision. They propose truly unsupervised image-to-image translation method by utilizing a guidance network. The proposed model successfully performs the task by using generated pseudo-labels and style-coded feature vectors. The link to the paper and some useful resources will be provided in the description. That's all for today, and I'll see you next time with a new paper.